Welcome back. In this video, we will discuss the technological developments that are necessary to improve and optimize the hydrogen combustion engine. The idea is to maximize the natural advantages while minimizing its drawbacks. I must tell you, all the parameters discussed in this video are currently being tested and the research is ongoing. Let's find out what are the main points being investigated. Remember that there is a strong issue around pre-ignition, knocking and backfiring. To avoid these combustion anomalies, the injection, mixing process and ignition will be crucial points. Basically, we are studying how to optimize injection, mixing and ignition to produce a hydrogen engine that meets the challenges regarding efficiency, performances and low pollution levels. All this without any combustion anomalies. Let's start by discussing how to limit combustion anomalies. Backfiring is a combustion that occurs in the intake ducts or when the intake valves are open. The wide flammability range combined with the low energy needed to ignite hydrogen are essential aspects that facilitate backfiring. With these characteristics, all that is needed is a hotspot somewhere in the engine, and we have the right conditions for backfiring to occur. It's important to master the injection process to produce the conditions that limit this type of combustion. This means developing an injection system adapted to hydrogen. There are different ways to limit backfiring. With indirect injection, you have to play with hydrogen injection timing. The idea is to make sure that all H2 injected in the ducts is driven to the cylinder. Another very effective way is by using direct injection. With direct injection, the injection occurs inside the cylinder, so we reduce the risk of having a fuel-air mixture in the intake ducts. The injection can occur during the intake stroke and after the valves are closed, depending on the injection pressure and injector static flow. To avoid pre-ignition, we count on the mixing process and the choice of a suitable spark plug. Indeed, we can avoid pre-ignition by limiting rich zones and hot spots. The internal cylinder charge motion must be adapted to optimize the mixing. All these factors, the injection system, the in-cylinder charge motion, the choice of the spark plug, will have a favorable impact on knocking as well. Now, let's talk about efficiency and emissions, mainly NOx. The idea is to maximize performances while limiting emissions and combustion anomalies by playing with the same inputs. Hydrogen combustion, just like any combustion, will require us to find the right trade-off. We just talked about combustion anomalies and how the intrinsic characteristics of hydrogen might promote combustion anomalies. Well, those same characteristics affect the efficiency and emissions of hydrogen combustion. For example, when the in-cylinder charge motion is promoted to limit combustion anomalies, the thermal losses to the walls increase and a loss in efficiency can be observed. So, working to limit combustion anomalies often leads to reduced performances. How to control emissions then? A first way to control NOx emission is the use of after-treatment devices like SCR system used in diesel engine. These devices must be adapted and scaled to the levels of engine out NOx emissions. The emissions will probably be lower than for diesel engines since the equivalent ratio working conditions are lower with H2. Dilution is a major technique used when trying to reduce emissions and meet efficiency targets. It can be done by using air or other methods such as EGR or even water injection. Dilution using air implies a decrease of equivalent ratio, and by reducing the equivalent ratio we can limit NOx and increase the engine's efficiency. Indeed, with low equivalent ratios, the peak temperature decreases and so does the amount of NOx. At the same time, a lower equivalent ratio limits the thermal losses with an increase in efficiency. However, to reach low value of equivalent ratio, we need high supercharging values. Dilution using EGR range is another way to decrease NOx. It requires to adapt the air loop of the engine. Since the exhaust gases have a higher charge of water, they act as a heat absorber and reduce the gradient of heat released that produces noise. Additionally, with a lower peak of heat released, the temperature is also controlled and NOx emissions are reduced. As EGR content is mainly water and air, dilution directly using water injection can be a solution with less impact on the engine air loop, but it implies the installation of a complete water injection system. Additionally, and if abnormal combustions have been eliminated, the volumetric compression ratio can be maximized to increase the theoretical efficiency. This is possible because of the high temperature of autoignition. However, increasing the volumetric compression ratio will produce higher levels of in-cylinder pressure with two main consequences. First of all, the engine itself must resist higher levels of thermomechanical stress, so it must be more robust. The engine base is therefore probably closer to a diesel one than a gasoline one. With the increase of in-cylinder pressure, the friction losses also increase. As you can easily understand, the increase of friction losses will reduce the engine's efficiency compared to a gasoline-based engine. Secondly, when the in-cylinder pressure increases, the temperature inside the cylinder also increases. As a result, the production of NOx emissions will be enhanced. Of course, the NOx issue is well known from the experience we have with this diesel engine. In extreme cases, high compression ratios could lead to combustion anomalies. Dilution by EGR, for instance, will help to control these anomalies. To give you some magnitude values, with volumetric compression ratio between 12 and 16, we are able to reach efficiency of 47% without producing any NOx for operating condition of 3000 RPM and 10 bar of IMEP. Now, let's talk about power output. Power output is directly linked to energy and air introduced in the engine. For energy, there is an issue regarding injection because we need to inject a maximum amount of fuel to ensure the right amount of energy in the cylinder during the minimum time possible while ensuring the mixing with the air. One of the parameters to study is the injection pressure. The injection pressure value is a trade-off. On the one hand, we want to increase the injection pressure so we can inject the fuel very quickly. The faster we inject, the more the performances in terms of efficiency and power increase. The maximal injection duration is limited, first, because we cannot begin to inject before the beginning of the intake phase. Second, because the end of the injection is driven by the ratio between injection pressure and in-cylinder pressure. The injection pressure must be higher than the in-cylinder pressure during the injection process. Therefore, if we increase the injection pressure, we can inject more fuel during this amount of time. So when we increase injection pressure, power increases because we can inject more fuel during the same amount of time, and thus we counteract the low energy density of H2. Remember that the energy content per volume is very low for hydrogen. To increase power, we can also increase the fuel flow capacity of the injector. That's another parameter to optimize. On the other hand, we want to keep the injection pressure as low as possible to take full advantage of all the hydrogen available in the pressurized tank. The injection pressure of hydrogen is usually lower than the pressure in the tank. Otherwise, we would need to add a system to compress the hydrogen in the engine. This is possible, but would add complexity to the injection system. Furthermore, autonomy is also an issue. Let's say that hydrogen is compressed at 300 bar in the tank. If we choose to inject at 100 bar, once we have consumed 2/3 of the hydrogen in the tank, we will need to refill it. Basically, without H2 compression system, the lower the injection pressure is, the higher the car's autonomy will be. For air, supercharging is a key point. It is important to adapt it to maximize the performances. By increasing the intake pressure, we can increase the performances. The supercharging needs to be optimized together with the injection system. If more air is admitted, then the injection system must be adapted consequently. In general, the more supercharging capacity you have, the more power you can produce with the engine. To produce high intake pressures, one solution is to use heat chargers. Finally, another way to increase power is to increase the volume displacement of the engine. And there you have another parameter to optimize. To finish, please remember, engine optimization is always a trade-off. When you improve one result, usually another result gets worse. It's extremely important to work on the system as a whole so that the global result is optimized. The key parameters to optimize are the injection system, the supercharging system, the in-cylinder charge motion, the compression ratio, and the volume displacement of the engine. They all influence the main performances of the engine, and trade-offs must be chosen carefully. With optimization, we can control combustion anomalies like pre-ignition knocking or backfiring while improving efficiency. At the end, thanks to engine and after-treatment optimizations, it will be possible to have a zero-emission engine with efficiencies above 45%. Thanks for watching!